Hello everyone, welcome to the channel. This is Dr. P Aerospace, and today we're going to be going over integral analysis, which is basically a component of the Reynolds transport theorem, and we're specifically going to look at the conservation of mass. So this should be a pretty straightforward lecture slash mini video, and we're going to go over one example problem, and hopefully in the next couple of videos we'll go into some more complex problems because this topic is pretty straightforward. But again, if you have any questions or comments, please go to the comment box below and leave your questions and I'll try to get back to you. So let's jump right into things. So you'll see at the top, the conservation of mass is actually, it just comes right from our Reynolds transport theorem equation, which I have listed out here. And as a quick reminder, just we'll do a quick recap. The Reynolds transport theorem is basically trying to bridge the gap between the Lagrangian and Eulerian fluid flow perspectives. And in this case, the left-hand side here with this term dn over dt of our system is going to be the Lagrangian term. And these two terms on the right-hand side here are going to be looking at a fixed region of space, which will be our Eulerian perspective. So that's, kind of our baseline starting point. And then also as a quick recap, the capital N here is our extensive property, and the eta term here is our intensive property, which is just equal to N divided by M, or extensive property per unit mass. So for conservation of mass, we basically just set our extensive property to M, which means that eta is equal to 1 based on this definition, and that's a really bad eta. It's kind of hard to draw that, but that's an eta symbol. And after that, we just plug it into our Reynolds transport theorem kind of skeleton equation here, and we get a relationship like this. Now, we can actually make one more simplification here, and it's based on kind of like the definition of a system that we had discussed in the previous video, which is also linked in the description again. But a system has a fixed mass and its fixed identity. So you can't have a change in mass with respect to time of a closed system. So in this case, your time rate of change of your mass is just equal to 0, which is represented by this term here, and you are left with this final relationship down here. Now, conservation of mass is also commonly known as the continuity equation. So this is just something to be aware of that some professors prefer to use, but most of the time they'll kind of use them interchangeably. So these two terms here, I realize that my little PNG self is off to the right, so I can't really write there, but I'll try to do my best to kind of break this down. This term right here, I'll call the rate of accumulation. It's basically the rate of mass that's being accumulated by the system. So I just usually like to call it the rate of accumulation term. And if you're not considering specifically conservation of mass, this is also called the unsteady term because you have this partial with respect to t. But as it pertains to conservation of mass or continuity, this is the rate of accumulation of mass within the control volume. And then next we have our flux term over here, right here. And this is going to basically just be the net rate of mass flux through the different control surfaces of our control volume. Cool. So it's pretty straightforward. And that's, I mean, that is the equation. Now, I will take a couple slides to go through some certain scenarios where we can actually simplify this and apply it to certain scenarios, depending on what the fluid is and what the kind of situation entails. But it's really not too bad. So let's go to case number 1 here, where we have incompressible flow. So for incompressible flow, things like like waters or very low speed gaseous flows that are just incompressible. Rho is just equal to constant. And if we go to our continuity equation form right here, what we can do first is, we can bring our rho's outside of our integration terms here because they are constant. And our relationship would look like something like this. Okay, and then after that, because rho is pretty much a constant here and it's outside the integral, you can technically just cross it out because if you divide both sides by rho, you'll be left with this relationship right here. And then our last final step is to basically just, bring this differential volume element outside of this integral here, and you're left with this final relationship right here, where this term in this current state is basically equal to, it's like a deformable control volume. That's basically what this is. That's all it is. So in certain situations where you would have, this is the most common one that I can think of is more of like a kind of beginner concept here. So you have like a cone that has a bunch of water here, and you suddenly just kind of like pop the lid off of this cone here, for example. You just kind of like opened it up. All of a sudden, you would have water begin to kind of drain out through the bottom, and this kind of volume of fluid here would technically be like going down in height, and therefore your volume is technically changing with time. So it would be hard to make like a control volume that's fixed here because your mass would just be continually going down. So your control surface at like the upper surface, for example, here would have to just kind of go at a constant rate down with the water as it drains. So we'll do a couple practice problems like this situation. This is very common actually for a situation where you have a deformable control volume, but that's what that term is. Then if we look at this term here, this is actually just going to be the volumetric flow rate, but written as an integration term as a dot product of v dot dA. So as a quick recap, your volumetric flow rate, q dot, is just equal to velocity times area. If we're not considering vectors there, it's a very simple v times a. So when you end up kind of evaluating this dot product term and you consider, your unit normal vector of your area vector, you'll just get a different sign of what q dot is depending on whether it's going into the control surface or out of the control surface. So nothing too crazy again. We'll work this out too so you can kind of understand what I was saying there if you are a little confused. Now, in a situation which is also very common in most undergraduate classes, where you have a non-deformable control volume, um, dv over dt, that term we discussed before, is just equal to 0. So we can cancel this out, and you're just left with that volumetric flow rate term that we had before, the q dot equals v times a. And after you evaluate it at like an inlet and an outlet, technically you would kind of break it down even further and basically just simplify it into the summation of your incoming volumetric flow rates is equal to the summation of your outgoing volumetric flow rates. And when we get to the practice problem at the end, this will make more sense because we're going to break down kind of how this actually goes from this to this. And finally, another common case is that you have steady compressible flow with a fixed control volume in time. In this case, for steady flows and a fixed CV, this entire term here will actually just go to 0. So we can knock that out of our equation, and you're basically just left with this flux term here. Now, as a reminder, your mass flow rate is equal to rho VA, or you can just say it's rho times Q dot, depending on how you want to write it, but that's essentially what you get from that. So this equation will actually simplify into the summation of your mass going into your control volume is equal to the summation of your mass going out of your control volume. So pretty straightforward relationship. For the example problem, I'm going to start at the more mathematically kind of rigorous definition of what the control surface like flux term is, and we'll eventually get to this relationship down here, especially in some of the more complex future problems where it's important to actually start with this term, especially when you're getting more comfortable with how it works. Okay, so let's move on to an example. Water flows steadily through the region shown below. At inlet 1, the velocity is 6 meters per second, and the area is 0.2 meters squared. At outlet 2, the velocity is 20 meters per second, and the area is 0.1 meters squared. What is the magnitude and direction of the water going through port 3 if the area of port 3 is equal to 0.04 meters squared? So this is a really simple and straightforward problem with a very well-defined region of space that we can define as our control volume. So let's first and foremost kind of define what our control volume is. So it's pretty much laid out here. Basically, this entire shape that you see here I think is a good shape to do our control volume. So basically everything you see in this dotted area here will be our control volume, where these kind of blue lines denoting the inlets and outlets will be our control surfaces of interest because they have mass transfer. So that's our CV. Next step is we want to list out some assumptions. And these assumptions are going to allow us to basically simplify the conservation of mass relationship. So assumption one, we have water here is our first word of the problem. So we know we're going to be using a incompressible fluid. And then we have steady flow. It's flowing steadily through the region. Okay. And then our control volume is fixed in time. Like these are walls here basically of a region. And we as the engineer, we're not, we're not going to kind of have this control volume and change in time. It's going to be fixed at this entrance, and these exits here. So this is actually a non-deformable control volume, which again is the case for like 99% of the problems you deal with. And finally, this is an assumption that is not explicitly stated in the question itself, but you can assume that there's uniform flow going into the inlets and exits because the problem is not really telling you there's like varying velocity. So in some example problems, which we'll get into probably after this video, there's might be a situation where you have like a very high velocity here compared to a very low velocity here, meaning you have to you know consider this variation in velocity across your control surface and include it in your integration term. So there's going to be some type of integration with respect to spatial coordinates there, but again, that's kind of out of the scope of this. We can assume here that this is a uniform flow. Great. Apologies for poor handwriting. I'm using a Wacom tablet. It's not super optimal, but it does the job for just getting the ideas across. So if you don't understand what I'm writing, just listen to what I'm saying, and I'm pretty much just reflecting that. So let's start off with the continuity equation. Let's write it out really quick. Del over del T of our integral for our control volume of rho dV plus our flux term here, which is across our control surfaces. This will be rho times the dot product of V dot dA, all equal to 0. So let's start canceling some things out based on our assumptions. So we know that we're incompressible, so density can be pulled out of the integrals, and we can divide both sides by density, and basically density just cancels out. First one, steady flow and non-deformable control volume. We determined that this would lead this entire term to become 0. And then finally, we have uniform flow, which just basically means, again, that velocity is not varying with area. So again, this term will become a little bit more apparent once we get into the practice problems where V does vary with the surface area. Okay, so let's continue here. So let's rewrite our relationship. Now, again, this is, very simple. All this is summation of Q dot in equals summation of Q dot out. But because, again, we're really trying to develop our kind of core fundamental concepts of how this turns into this, we're going to just quickly uh, evaluate these integrals at each of the control surfaces, just so you can see how we get this relationship here. And this same concept applies to like the, other versions of this, where, for example, you have compressible flow or something like that. So let's rewrite everything out here. So each of our control surface terms here will get its own nice integral. Just like that. And now let's try to evaluate the control surface here. So let's start off with control surface one. So let's put this down here. This is basically like our dA, and then we have. Just going to try to use some different colors here to mix it up. We'll have our unit normal vector pointing orthogonally outwards from our surface to the left. But you'll see if we look to our diagram up here, velocity is going to the right here. Use dark blue. And in this situation, your unit normal vector and velocity are pointed in opposite directions. So if you review like the dot product, that the cosine of our 180 degrees results in like a negative value. And also, it's important to note that when you do the dot product of like v dot n times the scalar value of dA of that control surface, this term right here just results, excuse me, in a scalar quantity. So this would just be something like v times dA. So nothing too crazy there. I won't explain this too much just because that's just kind of like the fundamental mathematics. There's probably plenty of videos out there that go over that. But the big thing I want to drive home is that your inflow is going to be negative because the unit normal vector is in the opposite direction as your incoming velocity. So basically we can just rewrite this integral as a minus CS1 of V1 times dA scalar quantity. Next we have our other term here. This is control surface 2. We have we have our unit normal vector pointed to the right in this situation because we have this surface right here. This will be dA as well, and then this will be dA2, excuse me. And then we have our velocity going to the right. So in this case, we have an outflow. We have our unit normal vector going in the same direction as our velocity. And therefore, the angle would be 0 between them. Cosine of 0 is positive 1. And your dot product term would just become a positive value there. So let's write this out again. This will be a positive integral of CS2 V2 times dA scalar quantities. And then we do the exact same thing with V3. I'm going to write it out, but I feel like you should get the gist at this point. This is dA3. Just because we're at an angle doesn't necessarily mean we're going to have any weird math, but n comes out this way, and velocity is assumed to go out this direction here. This is very redundant at this point, but I'm just going to finish it out. Again, n and v are going in the same directions, so we'll just get another positive term here. Okay, so this is our kind of final term here. Now, we can pretty much rewrite this in a very simple way because it seems A1 is fixed here, right? It just says like, for example, like inlet 1, 0.1 meters squared, 0.1 meters squared, or excuse me, 0.2 meters squared for inlet 1, 0.1 meters squared for outlet 2, and 0.04 meters squared for outlet 3. So dA, it is a differential area, but it's also a fixed value. So we technically, this is fixed, it's not changing, and V is also fixed. So we're not really having to integrate here, to be honest, because there's no really bounds of integration, and these are both kind of constants. So if that's the case, we can kind of just write this as minus V1A1 plus V2A2 plus V3A3 equals 0. If you pull this term to the other side here, you basically are left with this equation here. Because remember, Q is equal to V times A. And all we're saying is that all of our inflows are going to be negative, all of our outflows are going to be positive, and when you move them over to the other side, so you don't have any negatives in this equation, you just put everything on the other side where there is a 0, you end up with this relationship here. So that's where that comes from. Now we're trying to solve for V3, so let's move to the next slide really quick. So let's see, let me rewrite this really quick. V1A1 equals V2A2 plus V3A3. We're trying to solve for V3, so let's just quickly kind of position ourselves to do that. So move this over here and divide by A3. So that'll be V1A1 minus V2A2, all divided by A3. And when you plug all of these values in here, you'll see that V3 is equal to negative 20 meters per second, which, you're like, wait a second, Dr. P, there's an outward vector there, or an outward direction arrow. Why is it negative? Well, that's the fun thing about fluid mechanics and some of these assumptions. We technically assumed that we were getting an outflow velocity here, but by solving conservation of mass, we actually found our initial guess was not correct. So all we had was a change of our sign. So in this case, rather than be coming out, it's going into our control surface. That's all it is. But yeah, that's pretty much our final answer. So our magnitude is 20 meters per second and our direction is negative going into the control surface. Or you can just say, positive into control surface, something like that. That could be your other portion there. But yeah, that's pretty much it. So thanks everyone for watching. Stay tuned for some future videos. Next video, I'll be doing some practice problems where we actually try to evaluate some more complex terms, evaluate some of the integrals, and then eventually we'll get to a situation where we have like a deformable control volume. So yeah, thanks for watching. Catch you later.